A truth table is a mathematical table used in logic, specifically in connection with Boolean algebra, Boolean functions, and propositional calculus, to compute the functional values of logical expressions on each of their functional arguments, that is, on each combination of values taken by their logical variables. Practically, a truth table is composed of one column for each input variable, and one final column for all of the possible results of the logical operation that the table is meant to represent. Each row of the truth table therefore contains one possible configuration of the input variables, and the result of the operation for those values. See the examples below for further clarification. Ludwig Wittgenstein is often credited with their invention in the Tractatus Logico-Philosophicus, though they appeared at least a year earlier in a paper on propositional logic by Emile Leon Post. Unary operations. There are 4 unary operations. Logical false logical identity. Logical identity is an operation on one logical value, typically the value of a proposition, that produces a value of true if its operand is true and a value of false if its operand is false. The truth table for the logical identity operator is as follows. Logical negation. Logical negation is an operation on one logical value, typically the value of a proposition, that produces a value of true if its operand is false and a value of false if its operand is true. The truth table for not P is as follows. Logical true binary operations. There are 16 possible truth functions of 2 binary variables. Truth table for all binary logical operators. Here is a truth table giving definitions of all 16 of the possible truth functions of 2 binary variables. Enderton and Quine. For details about the operators, see the key below, where T equals true and F equals false. The com row indicates whether an operator, op, is commutative, P op Q equals Q op P. The L-id row shows the operator's left identities if it has any values I such that I op Q equals Q. The R-id row shows the operator's right identities if it has any values I such that P op I equals P. The 4 combinations of input values for P, Q, are read by row from the table above. The output function for each P, Q combination can be read by row from the table. Key. The key is oriented by column, rather than row. There are 4 columns rather than 4 rows, to display the 4 combinations of P, Q, as input. P, T, T, F, F, Q, T, F, T, F. There are 16 rows in this key, 1 row for each binary function of the 2 binary variables, P, Q. For example, in row 2 of this key, the value of converse non-implication is solely T, for the column denoted by the unique combination P equals F, Q equals T, while in row 2, the value of that operation is F for the 3 remaining columns of P. The output row for is thus 2. FFTF, and the 16-row key as logical operators can also be visualized using Venn diagrams. Logical conjunction. Logical conjunction is an operation on 2 logical values, typically the values of 2 propositions, that produces a value of true if both of its operands are true. The truth table for P and Q is as follows. In ordinary language terms, if both P and Q are true, then the conjunction PQ is true. For all other assignments of logical values to P and to Q, the conjunction PQ is false. It can also be said that if P, then PQ is Q, otherwise PQ is P. Logical disjunction. Logical disjunction is an operation on 2 logical values, typically the values of 2 propositions, that produces a value of true if at least one of its operands is true. The truth table for P or Q is as follows. Stated in English, if P, then PQ is P, otherwise PQ is Q. Logical implication. Logical implication, or the material conditional, are both associated with an operation on 2 logical values, typically the values of 2 propositions, that produces a value of false just in the singular case the first operand is true and the second operand is false. the truth table associated with the material conditional if P then Q, and the logical implication P implies Q is as follows. It may also be useful to note that PQ is equivalent to PQ. Logical equality. Logical equality is an operation on two logical values, typically the values of two propositions, that produces a value of true if both operands are false or both operands are true. The truth table for PXNORQ is as follows. So PEQQ is true if P and Q have the same truth value, and false if they have different truth values. Exclusive disjunction. Exclusive disjunction is an operation on two logical values, typically the values of two propositions, that produces a value of true if one but not both of its operands is true. The truth table for PXORQ is as follows. For two propositions, XOR can also be written as logical NAND. A logical NAND is an operation on two logical values, typically the values of two propositions, that produces a value of false if both of its operands are true. In other words, it produces a value of true if at least one of its operands is false. The truth table for P NAND Q is as follows. It is frequently useful to express a logical operation as a compound operation, that is, as an operation that is built up or composed from other operations. Many such compositions are possible, depending on the operations that are taken as basic or primitive, and the operations that are taken as composite or derivative. In the case of logical NAND, it is clearly expressible as a compound of not and in. The negation of a conjunction, and the disjunction of negations, can be tabulated as follows. Logical NOR. The logical NOR is an operation on two logical values, typically the values of two propositions, that produces a value of true if both of its operands are false. In other words, it produces a value of false if at least one of its operands is true. Is also known as the Pierce arrow after its inventor, Charles Sanders Peirce, and is a sole sufficient operator. The truth table for P NOR Q is as follows. The negation of a disjunction, and the conjunction of negations can be tabulated as follows. Inspection of the tabular derivations for NAND and NOR, under each assignment of logical values to the functional arguments P and Q, produces the identical patterns of functional values for as for, and for as for. Thus the first and second expressions in each pair are logically equivalent, and may be substituted for each other in all contexts that pertain solely to their logical values. This equivalence is one of De Morgan's laws. Applications. Truth tables can be used to prove many other logical equivalences. For example, consider the following truth table. This demonstrates the fact that PQ is logically equivalent to PQ. Truth table for most commonly used logical operators. Here is a truth table giving definitions of the most commonly used 6 of the 16 possible truth functions of two binary variables. Key. T equals true, F equals false equals an equals or equals XOR equals XNOR equals conditional, if then, equals conditional, if biconditional or, if and only if, is logically equivalent to XNOR. Logical operators can also be visualized using Venn diagrams. Condensed truth tables for binary operators. For binary operators, a condensed form of truth table is also used, where the row headings and the column headings specify the operands and the table cells specify the result. For example, Boolean logic uses this condensed truth table notation. This notation is useful especially if the operations are commutative, although one can additionally specify that the rows are the first operand and the columns are the second operand. This condensed notation is particularly useful in discussing multi-valued extensions of logic, as it significantly cuts down on combinatoric explosion of the number of rows otherwise needed. It also provides for quickly recognizable characteristic shape of the distribution of the values in the table, which can assist the reader in grasping the rules more quickly. Truth tables in digital logic. Truth tables are also used to specify the functionality of hardware lookup tables in digital logic circuitry. For an n-input LUT, the truth table will have 2n values, completely specifying a Boolean function for the LUT. By representing each Boolean value as a bit in a binary number, truth table values can be efficiently encoded as integer values in electronic design automation software. For example, a 32-bit integer can encode the truth table for a LUT with up to 5 inputs. When using an integer representation of a truth table, the output value of the LUT can be obtained by calculating a bit index k based on the input values of the LUT, in which case the LUT's output value is the kth bit of the integer. For example, to evaluate the output value of a LUT given an array of n Boolean input values, the bit index of the truth table's output value can be computed as follows. If the ith input is true, let, else let, then the kth bit of the binary representation of the truth table is the LUT's output value, where truth tables are a simple and straightforward way to encode Boolean functions. However, given the exponential growth in size as the number of inputs increase, they are not suitable for functions with a large number of inputs. Other representations which are more memory efficient are text equations and binary decision diagrams. Applications of truth tables in digital electronics and computer science. Truth tables can be used to reduce basic Boolean operations to simple correlations of inputs to outputs, without the use of logic gates or code. For example, a binary addition can be represented with the truth table A, B, C, R11, 1010, 0101, 0100, 00, where A equals first operand, B equals second operand, C equals carry, R equals result. This truth table is read left to right. Value pair equals value pair, or for this example, A plus B equal result R, with the carry C. Note that this table does not describe the logic operations necessary to implement this operation. Rather, it simply specifies the function of inputs to output values. With respect to the result, this example may be arithmetically viewed as modulo 2 binary addition, and is logically equivalent to the exclusive or binary logic operation. In this case it can be used for only very simple inputs and outputs, such as 1s and 0s. However, if the number of types of values one can have on the inputs increases, the size of the truth table will increase. For instance, in an addition operation, one needs 2 operands, A and B. Each can have one of 2 values, 0 or 1. The number of combinations of these 2 values is 2 times 2, or 4. So the result is 4 possible outputs of C and R. If one were to use base 3, the size would increase to 3 times 3, or 9 possible outputs. The first addition example above is called a half adder. A full adder is when the carry from the previous operation is provided as input to the next adder. Thus, a truth table of 8 rows would be needed to describe a full adder's logic. A, B, C asterisk, C, R, O, 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 1, O, O, 1, 1, O, 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 1, 1, 1, O, 1, O, 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 1, O, 1, O, 1, 1, 1, O, 1, O, 1, 1, O, 1, 1, 1, 1, 1, same as previous, but C asterisk equals carry from previous adder history. Irving and Ellis has done the research to show that C.S. Piesk appears to be the earliest logician to devise a truth table matrix. From the summary of his paper, in 1997, John Shosky discovered, on the verso of a page of the typed transcript of Bertrand Russell's 1912 lecture on the philosophy of logical atomism, truth table matrices. The matrix for negation is Russell's, alongside of which is the matrix for material implication in the hand of Ludwig Wittgenstein. It is shown that an unpublished manuscript identified as composed by Piesk in 1893 includes a truth table matrix that is equivalent to the matrix for material implication discovered by John Shosky. An unpublished manuscript by Piesk identified as having been composed in 1883–84 in connection with the composition of Piesk's On the Algebra of Logic, A contribution to the philosophy of notation, that appeared in the American Journal of Mathematics in 1885, includes an example of an indirect truth table for the conditional.